Welcome to Calculus 1 class. Today we're going to talk about continuity and one-sided limits. So let's begin with continuity at a particular point. Now, by definition, we say that a function f is continuous at x equal to c. That means that there is no interruption in the graph of the function at c. Alright, continuity means the whole function is continuous. Okay, 3x equal to c. There's no interruption whatsoever. So the function f is not continuous at c, okay, in the following way. So let's say I have an open interval from a to b, and here is my function, okay, from a to b, and there exists a number c inside the interval. So my function is not continuous, okay, can be drawing in this fashion. Okay, I'll use an open circle for a and b because it's an open interval. I have an open circle here at x equal to c because f is not continuous at c. Alright, another way where the function f is not continuous, if the limit of the function as x approaching to c, okay, does not exist. The limits of the function as x approaching to c does not exist. D and E. Alright, it's not continuous because in an open interval a and b there exists a number c where my function, okay, goes up approaching to c with a solid circle, and there's another part of my function with an open circle that is going to the end of the interval b. Alright, so my limit does not exist because one part of the function exists at c. The other part of this same function does not. It's actually the limit is actually with the open circle. Alright, so that will actually make the limit of the function does not exist. Okay, it gotta exist in both part of the same function. Alright, another way where the function does not where the limit does not exist, or the function is not continuous, is when the limits of the function as x approaching to c that would not equal to, that cannot be evaluated at f of c. Okay, what that means is between the interval a to b there exists a number c where my function as approaching to c, okay, has an open circle at c. Alright, and at the end of the function inside the interval to b, alright, open circle again. But when I evaluate f of c, the y value actually is somewhere else. Okay, if that's the case, alright, the function is not continuous. So what that tells us is a function f is continuous at c when these three conditions got to be met. Number one, f of c is going to be defined. Okay, I got to be able to define f of c. In this first picture, f of c is actually not defined. Because my function, I cannot evaluate my function at c. Alright, so for a function to be continuous, f of c got to be able to be, we got to be able to define f of c. The limit of the function as x equals to the c got to exist, And the limit of the function as x approaching c got to equal to f of c itself. Alright, so these three conditions are going to be met for us to say that f is actually continuous at c. Alright. So second objective, continuity on an open interval. We say that a function f is continuous on an open interval from a to b when the function is continuous at each point inside that interval. Okay. Every single point in between a to b got my function got to be continuous between a to b in this open interval. For example, polynomial function like x to the third. Alright, we know the domain for a polynomial function is from negative infinity to infinity. Alright, so it actually turns out the function is continuous at every single point within this interval. Alright, so my function is continuous everywhere within its domain. Alright, a rational function, 1 over x. Now we know the domain is all real number because I know my x cannot equal to 0 in the denominator. Alright, so domain is all real number except at x equal to 0. So at x equal to 0, my function f has what we so called a non-removable discontinuity. So there is no way to define f of 0. I cannot substitute 0 inside this function so as to make the function continuous. There's nothing I can do, alright, to make this function continuous at x equal to 0. That is called non-removable discontinuity. Alright, what is so called the removable discontinuity. Alright, this function, for example, x squared minus 1 over x minus 1. If I will graph this function, as you can see, when x equal to 1, my y value is an error. I can actually type in this whole function into the calculator, and this is what we'll say on the table. So I know the domain is all real number except at x equal to 1. However, though, this time at x equal to 1, my function f has a removable discontinuity by defining f of 1 as 2. So what that means is I can actually redefine this function where at x equal to 1, my y value will be 2. So the redefined function is continuous for all the real numbers. Alright, so I can actually redefine my function because if you really think about it, this is a rational function, but when I graph it, it actually becomes a linear function. It looks like a straight line. Okay, even though when I type in this function at x equal to 1 give me an error, but I can actually redefine this function to make it into a new function, and for this new function, which is a linear function, okay, the new function is actually continuous for all the real numbers. And there's actually a theorem actually can make that true as well. I'm trying to see if we talked about that before. Yes, we have. We actually have talked about it, something like that before. Okay. Function that agree at all but one point. The new defined function, okay, this new defined function is equal to the original function. So what I could have done is to factor the numerator and give me x plus 1 times x minus 1, and that will allow me to cancel out with my denominator, x minus 1. So this new redefined function is simply x plus 1, and that redefined function, alright, is continuous at x equal to 1. continuity. Now, back to limits. I'm going to introduce here what's so-called the one-sided limits. Okay, there are two types for the one-sided limits. Limit from the right versus limit from the left. Limit from the right means that x approaches c from the value greater than c. Okay, that will be from the right hand side. Number bigger than c will be to the right hand side. Alright, so the limit of the function as x approaching to c from the right hand side will equal to L. Alright, limit from the left means x approaching to c from the value less than c, that will got to be from the left side. Okay, so we will say it this way: limit of the function as x approaching to c from the left is also equal to my limit L. So for the existence of a limit, okay, function f be a function and let c and L be real numbers. The limit of the function as x approaching to c is L if and only if, okay, the limit of the function as x approaching to c from the left, okay, got to equal to L. So is the limit of the function from the right got to also equal to that same number. Okay, so as a limit coming from the right and left, okay, they all got to approach into the same limit. Okay, for us to say there is an existence of a limit. Alright, when the limit from the right side is not equal to the limit from the left side, then the limit does not actually exist. Alright, so check it out. For this example, remember now, limit from the right and the limit from the left, okay, got to be the same thing. Otherwise, the limit does not exist. So let's take a look at the limit of this function as x approaching to 4 from the right hand side. If I will graph it, this is an absolute value function. So math, highlight numbers, number 1, ABS, absolute value of x minus 4, close parenthesis, divided by x minus 4 is 2 terms. Let's put that in the parenthesis. Okay, and let me change my window. Excuse me. Oops. Let me go back to standard window. Alright, so this is what it looked like. I'm gonna shrink this y-axis down a little bit. I'm gonna go from -5 to 5 for my y. Alright, so check it out. Alright, so as x approaching to 4 from the positive side, 1, 2, 3, 4. This is 4. Approaching to 4 from the right hand side. So as my x keep on coming towards 4 from the right hand side, that tell me my y value or my limit is actually going to be +1. Now if I will go from the left, which is this right here, as x approaching to 4, my limit is actually going to be -1. So the limit from the right is not the same as limit from the left. Therefore the limit of this function as x approaching to just 4 does not exist. Does not exist. Okay, the limit from the right and left got to be the same. Alright, otherwise the limit does not exist. Alright, let's try another example here. Find the limits of the cotangent of x as x approaching to pi. So if I will graph this function, cotangent, cotangent is inverse of tangent, so we will do 1 over, okay, 1 divided by, I'm going to put my tangent in a parenthesis, okay, 1 divided by cotangent of x. I'm going to do close one parenthesis for the variable, close one parenthesis for the bottom I opened it. Alright. And I'm going to do my window starting at 0, and I'm going to go look at it as 2 pi. X maximum is 2 pi, period. X scale, I'm going to do pi over 4. I'm going to do negative 5 to 5. Alright. And this is what my cotangent looks like. So from the trigonometry class, as you can recall, okay, for the cotangent, there's a vertical asymptote, okay, at every interval of pi. There's a vertical asymptote at every interval of pi. Alright, so what that tells me is I have a vertical asymptote. Let me draw a line right here. Alright, 1, 2, 3, about 3.14. About 3.14, there's a vertical asymptote. Alright. At 3.14, there's a vertical asymptote. At 2 pi, there's also another vertical asymptote. Okay. And of course, there's a one at x equal to 0 as well. Alright. So, if we look at it, if this first one is approaching to pi, if this first red line here is my vertical asymptote at pi, as x approaching to pi from the right from the right hand side, my function is actually increasing without bound. This thing is actually going up. The other side, approaching from the left, my function is actually decreasing without bound. Okay, so since the right side is going up, left side is going down, decreasing without bound, that means the limit is not the same from the right and the left. So my limit of my cotangent x as x approaches to pi does not exist. And we will talk more about what does that mean, increase without bound versus decrease without bound as well in the next video. Alright, the point I want to make here is the limit from the right versus the limit from the left got to be the same, okay, for the limit to exist. Alright, let's take a look at this one last objective. Oh, I'm missing something here. Objective number 4. I don't have 4 here. Let me just kind of insert it real quick. Objective number 4 on your handout is continuity on a closed interval. We'll talk about this real quick. Continuity on a closed interval. Alright, a function is continuous on a closed interval if it is continuous in the interior of that closed interval, and the function has a one-sided continuity at the endpoint. Okay, I will show you graphically with this example. Alright, so what the theorem is basically saying is a function f is continuous on a closed interval from A to B with a bracket, that's a closed interval. If it is continuous on the open interval, A to B, and the limit of the function as x approaches to A from the right hand side will equal to f of A, and the limit of the function as x approaching to another value B from the left side can be evaluated at f of B, or my limit is at f of B. Alright, the function f is continuous from the right at A, and it's continuous from the left at B. So it got to be continuous, okay, within that closed interval. Alright, I'm going to show you this graph right here, real interesting graph. Square root of 1 minus x squared, close parenthesis. I'm going to zoom number 6, go back to my standard window. Alright, this is what it looks like as a standard window, so I need to kind of manipulate my window a little bit. I'm going to go from -2 to 2, not y value. Let's go do the same thing, -2 to 2. Alright, now that's much better. Alright, so if you look at this function, if you look at this, the graph of this function, on one side is -1, this is -1, this side right here is 1. So if you think about the limit of this function as x approaching to -1 from the right hand side, okay, that's my limit of the function approaching to -1 from the right hand side, okay, that will actually turn out to be 0, okay, because my y value here is 0. So that means if I will evaluate this function at -1, okay, if I plug in -1 here, okay, my limit will be 0. Now let's look at as the limit of this function 1 minus x squared as x approaching to +1 on the left hand side. We will notice that the limit will also be 0 again. So at the same time, if I will substitute 1 into the function, okay, the y value will be 0. Alright, so as you can see, if this function is continuous, okay, on the closed interval -1 to 1, because my function is continuous on the open interval from -1 to 1. Alright, that's what this concept is trying to say. Alright, so the domain of this function, remember now, the domain of this function is only from -1 to 1 in a closed interval. What we want to see is if the function f of x is continuous from -1 to 1 in an open interval. And to show that, we have to find the limits, okay, of the function evaluated at 2 different points, okay, evaluate 2 different numbers from the right hand side and 1 from the left hand side. Okay, if the limit is the same, okay, if the limit is the same for the right hand side and the left hand side, that tells me that the function is actually continuous on this closed interval, -1 to 1. Alright. Alright, properties of continuity, okay. Property of continuity. If b is a real number and my function f of x and another function g of x are continuous. Both of these are continuous at x equal to c. Okay. Then the following function are also continuous at c. So if I take this real number times my function f of x, scalar multiple. Okay. If I have a number in front of my function and multiply it, since my f of x is continuous at c, this new function is also continuous at c. Alright, since my two functions are continuous at c, if I add them up or subtract them, okay, the new function will also be continuous at c. Same thing for multiplication, same thing for quotient, except when I evaluate the c, my denominator still cannot equal to 0. Alright, so these four things are true because my two functions f and g are already continuous at c. Then the product, the quotient, the sum and difference, and scalar multiple will also be continuous. Alright. Continuity of a composite function. If a function g is continuous at c and function f is actually continuous when the g is being evaluated at c, then the composition of functions, okay, then my composite functions will also be continuous at c. Alright, so my function g of x is continuous at c. Alright, so if I substitute my g of x into my function f and evaluate at c, alright, well, my function f, my function f of x is actually continuous when I evaluate at that number, g of c. That means I gotta already substitute g of c into, that means I gotta already figure out what g of c is. Okay. Then I can what? Then I can substitute into my function f. If that's also continuous at that point, then the composition of function is also continuous. Alright, just some of these theorems. Now this example is very neat. Describe the intervals on which the function is continuous. My function here is tangent of x. Okay, I wrote this down so we can remember that the tangent function has a vertical asymptote at every odd multiples of pi over 2. So that means if I will do it for the positive side, that will be pi over 2, 1 pi over 2. The next vertical asymptote will occur at 3 pi over 2. The next one will be 5 pi over 2, so on and so forth. Okay. So I have interruptions, okay, or I have vertical asymptotes, make my function discontinuous at these, okay, when x is equal to these values. So if you think about it, alright, every r multiples of pi over 2. So this is 1 pi over 2. The next one is odd. So that tells me that my x cannot be, or the vertical asymptote is going to be at every odd multiple of pi over 2. Alright, so how do I describe the following one? If I got pi over 2 here, how do I describe 3 pi over 2? And then 5 pi over 2, so on and so forth. So what I can do is by saying x cannot be pi over 2 plus an integer n times every pi, where n is an integer. Alright, let me show you what I mean by that. If you think about it, the first one is at pi over 2, right? To go from pi over 2 to 3 pi over 2, all I gotta do is plus a pi. Oops, plus a pi. Because 2 times pi is 2 pi. 2 pi plus pi will make it 3 pi. Alright, so this pi over 2 plus pi is 3 pi over 2. Now, what happened if I start out with pi over 2 again? Alright, what do I need to add to make it into a 5 pi over 2? And this is where the integer n comes in, because right in front of this pi there's a number 1, The next one would be 2. So if I will plus 2 pi, 2 times 2 pi is 4 pi. 4 pi plus pi will make it 5 pi over 2. Okay, that's what the integer n is here for. Okay, if the integer is 0, if the integer n is 0, that would just be pi over 2. That's my starting point. Pi over 2, 3 pi over 2, 5 pi over 2. Okay. Alright, so my x cannot be pi over 2 plus n pi. So my function is continuous in the interval of, so this tangent of x is continuous in the interval of, let me write it this way, dot 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 is continuous from negative pi over 2 to pi over 2. And then the next interval where it is continuous will be from pi over 2 to 3 pi over 2. Alright, then the next interval will be continuous will be from 3 pi over 2 to 5 pi over 2. And then from 5 pi over 2 to the next R1, so on and so forth. So the way I'm going to describe it is simply by saying it will be continuous in these intervals. Okay, there's a lot more. There's actually a lot more. All right, but this is as much as I will write. Alrighty, so continuity and the one-sided limit. All right, that will conclude this video. Thank you for watching.